Good afternoon, everyone. My name is Dr. Miller, and the SCP we're going to be looking at today is SCP-2918. Object Class: Safe.
Course
Special
from
containment
Harvard
procedures.
University explores the concepts and algorithms at the foundation of modern artificial intelligence, diving into the ideas that give rise to technologies like game-playing engines, handwriting recognition, and machine translation. You'll gain exposure to the theory behind graph search algorithms, classification, optimization, reinforcement learning, and other topics in artificial intelligence and machine learning. Brian Yu teaches this course.
And we'll get more into that information later. I'll break down structures, creation,
Consisting of one airframe, one ground control system, GCS, and one primary satellite link communication suite, currently disabled. The GCS is configured into 4 cockpits to communicate with up to 4 airframes, but burn damage and ordnance fragmentation has rendered 3 out of 4 cockpits inoperable.
This course picks up where CS50 itself leaves off and explores the concepts and algorithms at the foundation of modern AI.
We'll start with a look at how AI can search for solutions to problems, whether those problems are learning how to play a game or trying to find driving directions to a destination. We'll then look at how AI can represent information, both knowledge that our AI is certain about, but also information and events about which our AI might be uncertain. Learning how to represent that information, but more importantly,
The nature of these messages imply that the airframe is
solutions as well. We'll explore how AI can solve various types of optimization problems, trying to maximize profits or minimize costs, or satisfy some other constraints, before turning our attention to the fast-growing field of machine learning, where we won't tell our AI exactly how to solve a problem, but instead give our AI access to data and experiences so that our AI can learn on its own how to perform these tasks. In particular, we'll look at neural networks, one of the most popular tools in modern machine learning, inspired by the way that human brains learn and reason as well, before finally taking a look at the world of natural language processing. So that it's not just us humans learning to learn how artificial intelligence is able to speak, but also AI learning how to understand and interpret human language as well. We'll explore these ideas and algorithms, and along the way, give you the opportunity to build your own AI programs to implement all of this and more.
In the
This
process, the
is
GCS
CS50.
was damaged, and the other airframes eventually crashed, not being able to receive commands to return and being unable to refuel. Their wrecks displayed no anomalous properties and were eventually scrapped. Though SCP-2918 has not displayed any independent motion since incident SCP-2918 Kanto, it is stored unarmed and unfueled as a standard safety precaution. No experimentation involving fueling SCP-2918 is to be undertaken at this time. Interview log SCP-2918, 51. Note: all psychiatric interviews are conducted through the GCS control panel. As such, SCP-2918 is rendered as UAV-A2, and Dr. is rendered as Pilot A2.
And we know that the probability of the blue die rolling a 6 is 1 over 6. So in this case, the conditional probability seems fairly straightforward, but this idea of calculating a conditional probability by looking at the probability that both of these events take place is an idea that's going to come up again and again. This is the definition now of conditional probability, and we're going to use that definition as we think about probability more generally to be able to draw conclusions. This again is that formula. The probability of A given B is equal to the probability that A and B take place, divided by the probability. And you'll see this formula sometimes written in a couple of different ways. You could imagine algebraically multiplying both sides of this equation by the probability of B to get rid of the fraction, and you'll get an expression like this. The probability of A and B, which is this expression over here, is just the probability of B times the probability of A given.
Would you like to
we
draw
could represent this
pictures today?
equivalently, since A and B in this expression are interchangeable. A and B is the same thing as B and A.
Interview
You could
log
imagine also
SCP-2918,
representing the probability of A
Kanto 1.
and B as the probability
Interview
of A
dated 19,
times the probability of B given A,
2000.
just switching
2
all of
days
the A's and
after
B's.
SCP-2918
These 3 are all
displayed
equivalent ways of
anomalous
trying to
properties.
represent what joint
Interview.
probability means.
Research.
So you'll sometimes see all of
A
these
prior
equations,
service member
they
and
might be useful to
Foundation
you
personnel
as you begin to
stationed at a
reason about
nearby
probability
AFB.
and to think about what
Interview
values
Captain
might be taking
Derek
place
Kanto,
in the real world.
USAF drone pilot.
Now, sometimes when we deal with probability, we don't just care about a Boolean event, like did this happen or did this not happen? Sometimes we might want the ability to represent like variable values in a probability space, where some variable might take on multiple different possible values. And in probability, we call a variable in probability theory a random variable. A random variable in probability is just some variable in probability theory that has some domain of values that it can take on. So what do I mean by this? What I mean is I might have a random variable that is just called roll, for example, that has 6 possible values. Roll is my variable, and the possible values, the domain of values that it can take on, are 1, 2, 3, 4, 5, and 6. And I might like to know the probability of each. In this case, they happen to all be the same, but in other random variables, that might not be the case. For example, I might have a random variable to represent the weather, for example, where the domain of values that take on are things like sun, or cloudy, or rainy, or windy, or snowy, and each of those might have a different probability. And I care about knowing what is the probability that the weather equals sun, that the weather equals clouds. And I might like to do some mathematical calculations based on that information. Other random variables might be something like traffic. What are the odds that there is no traffic, or light traffic, or heavy traffic? Traffic in this case is my random variable, and the values that random variable can take on are here. It's either none, or light, or heavy. And I, the person doing these calculations, I, the person encoding these random variables into my computer, need to make the decision as to what these possible values actually are. You might imagine, for example, for a flight, I care about whether or not I make it to a flight on time. My flight has a couple of possible values that it could take on. My flight could be on time, my flight could be delayed, my flight could be canceled. So flight, in this case, is my random variable, and these are the values that it can take on. And often I'll want to know something about the probability that my random variable takes on each of those possible values. And this is what we then